So we've been talking about how to do a control volume analysis, conservation of mass, or mass balance equation, linear momentum equation, where sum of forces can increase or decrease the linear momentum flow rate through the control volume, and likewise angular momentum. So we could have an angular momentum balance where a sum of moments acting on a control volume can increase or decrease the linear momentum flow rate of the fluid through that control volume. And then the key to this class, solve many problems and apply the concepts. So here are the starting equations for the general Reynolds transport theorem, and then you have it applied to a control volume for the conservation, or not really conservation, but linear momentum balance. Okay, so forces can increase or decrease the linear momentum flow rate through the control volume, or the linear momentum in the control volume with respect to time. Let's solve a problem. So the problem reads, laminar flow in a long circular tube has a parabolic velocity profile as a function of radius r, and cap r is the radius of the tube. You might want to sketch a little illustration. Here's the center line, and r goes from 0 to cap r at the wall. And the velocity profile is shown as being this profile. When you plot it, it'll be a quadratic, or what they call parabolic. It'll be maximum at the center line. It'll have that type of shape, a bullet type of shape. The first part of the multi-part sequence of questions is calculate the average velocity. Well, the average velocity, the average velocity, v(a)(b)(g), would be calculated by the equation 1 over the area, the integral of u dA. So that if you multiplied the average velocity, can't spell today, if you multiplied the average velocity times the cross-sectional area, you would get the volumetric flow rate through that any cross-section in the pipe. So what do? We substitute for u, and we perform this integral. And we're going to perform this integral in a coordinate system which is circular. So go ahead and look at the end of the pipe. There's the center line, and think about rings of fluid that have the same speed coming down the axis of the pipe in that little ring. So the area is 1 over pi r squared. The integral of u max, 1 minus lowercase r over cap r squared, times the area of a ring, and then we'll sum them up, 2 pi r dr, integrate with respect to r from 0 to cap r. Does that look reasonable? Okay, at this point, can I cancel the pi's? And can I bring that r squared and distribute it here and there? And can I take the u max out because it's constant? And so what we're left with is equation for u average. I guess I switch between u and v. U average is equal to the integral, well, u max times the integral from 0 to r, 1 minus r over cap r squared. I'm going to put a 2 here, and then I'm going to put lowercase r over cap r, derivative lowercase r over cap r. That 2 I should also move outside. Let me move that 2 outside the integral as well. So let's move that 2 out. So I have 2 u max, etc. At this point, you substitute. Let x, a new variable of integration, equal r over cap r. And then what you find is that this integrand becomes the 1 minus x squared times x dx. And we integrate then the lower limit. X lower limit is when r is equal to 0. Well, that's x equal to 0. And then at the upper limit, when r is equal to cap r, x is equal to 1. All right, so now we have to do that integral. Well, this is going to be the integral from 0 to 1 of x minus x cubed. True or false? Look good? Let's go ahead and do that integral. I need to move up here a little bit. Maybe I'll get rid of this line and come up here. So it's equal to 2 u max. It's going to be 1/2 x squared minus 1/4 x to the 4, evaluated 0 to 1, 2 u max. And then what do we have? 1/2 minus 1/4 is 1/4. And so u average is equal to u max divided by 2. So if you think about the length from this point to that point is a visual representation of the maximum speed, then the average is cut it in half, and u average is half of the maximum. So there's an answer for part A. Let's continue on then.
I have a question.
So this is a summary of what we did for part A. I need a clean sheet, so I decided to do it this way. And now let's calculate the mass flow rate. So somebody says calculate the mass flow rate. You have parabolic flow in a tube, and you know the velocity profiles like that. And given, so we would say, well, the mass flow rate is the sum of the little mass flow rates that are each going through each ring. Think about doing sums over the rings. Why? Because for each ring they have a constant velocity, constant speed. And so what is the mass flow rate in each ring? It's going to be rho times the area of the ring, which is 2 pi r dr, times the velocity u in that ring, and that's a function of r. So it's integral of rho u max 1 minus r over cap r squared times 2 pi r dr. True? Did I do it okay so far? Did I leave anything out? Mess anything up? And at this point, if you wanted to, you could do this. Pull that pi out of the integral. Pull the r out, the rho out of the integral. Pull the 2 out of the integral. Okay? And then also multiply by r squared over r squared. So what we'll pick up is we'll pick up a 2 pi r squared rho, and then we'll have the integral. Well, actually, I'm going to pull out u max as well. U max. Pull u max out as well. And then we'll have the integral of 1 minus lowercase r over cap r squared times lowercase r over cap r times derivative of lowercase r over cap r. And instead of integrating from 0 to cap r, we integrate from 0 to, well, we still do cap r, but we're going to now do the substitution. So the mass flow rate is 2, what is this pi r squared? The area. Times rho times u max. All right, then we're going to have the integral from 0 to 1, 1 minus x squared x dx. Hey, I've done that integral. True? What did we say that this integral was equal to? It was 1/2 or 1/4? Is it 1/4? 1/2 minus 1/4? So it's 1/4. So it's 1/4, true? And so m dot is equal to rho A U max divided by 2. But what is U max divided by 2? It's equal to rho A U average. And that's what we use all the time. If we wanted to know the mass flow rate down a pipe, we'd say, or a tube, we'd say, give me the mass density, give me the cross-sectional area, and give me the average speed down the axis of that pipe or tube. And you would be able to calculate the mass flow rate. All right. Ready to do another one? Well, we did this one, and we did this one. And now, clean sheet of paper, let's talk about calculating the linear momentum flow rate, and then calculate the momentum correction factor. Well, what symbol would we like to use for either part C or part D? What is a symbol that we like to use for linear momentum flow rate? I mean, we used m dot as mass flow rate, didn't we? Well, I don't know if there's a really great simple symbol used for linear momentum flow rate. Okay, so let's just say I'm going to calculate the linear momentum flow rate. When in doubt, make one up. All right. What about the momentum correction factor? Did they have a symbol for the momentum correction factor? Beta. So we're interested in calculating something, linear momentum flow rate down the pipe, and then beta. Now somebody says, if I had to calculate it without using calculus, without doing an integral, that linear momentum flow rate would be beta times the mass flow rate times U average. True or false? Is that how you would calculate the linear momentum flow rate down the pipe? You say, if you give me beta, you give me the mass flow rate, and you give me the average speed, I've got the linear momentum flow rate. True? Okay, so that's kind of a roadmap, but let's start off and say, from first principles, what is the linear momentum flow rate for flow down a pipe? It would be the sum of the linear momentum flow rates from little chunks of equal speed fluid going down, and because they have equal speed, they have equal linear momentum flow. Okay, so think again of that pipe, the center line. I know you get tired of drawing it. Look at concentric rings. Why do we sum up over all those rings? Because they have the same mass flow rate, the same U, the same linear momentum flow rate for that ring. It all has the same speed. All has the same speed in that ring. Okay, so what I'd have is I'd have the integral of U d m dots. For each ring, it has so much mass flow rate through that ring. I multiply by its velocity of that ring, and then boom, I can sum it up over there. So, okay, so that's the integral. What was the mass flow rate? It was the density times U times the dA. And so what we find is we have rho U squared dA, which is 2 pi r dr. And then when you have r, now we're going to integrate. R goes 0 to cap r. All right, might as well substitute what this U is as a function of r. I can substitute U max, or you know what we can do is we can substitute for U max, we could put 2 times U average, right? 2 times U average times blah, blah, blah. 1 minus lowercase r over cap r squared. That's also the way to express U. So either one, I just don't want to get too bogged down, and here it is. So it'll be 2 times U average times pi. Well, 2 pi, I pulled the 2 pi out. 2 pi. Okay? And then we have the integral of 1 minus r over cap r squared, quantity squared, times r dr. I pause. I may have tried to do too much in that. Maybe not. I'll introduce a cap r squared right there and put over r and put over r right there. Then we'll change variables so that we have the linear momentum flow rate is equal to rho, let's say 4 u average pi r squared, integral from 0 to 1 minus x squared times x dx. All right. How are we going to do this integral? Let's go ahead and say it's the integral from 0 to 1 of 1 minus 2x squared plus x to the 4 multiplied by x dx. The integral 0 to 1 of x minus 2x cubed plus x to the 5th dx. I'm going to pause for a minute. I'm going to see. Give me a thumbs up if you agree. Otherwise, ask me a question where I may have made an algebraic error. I don't want to go any further if I have an error. So I know that we covered a lot of ground, but now we can do that integration a lot easier, can't we? So isn't this 1/2 x squared minus 2/3, 2/4, isn't it? 2/4 x to the 4 plus 1/6 x to the 6th. Is that right? Evaluate 0 to 1, so that's going to be 1/2 minus, 1/2 plus 1/6. I'm going to stop right there. From here to there, those next two steps. Do you agree? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Thank you very much. 10 is good enough, okay? So, does that just boil down to a 1/6? So now we're ready to start grouping things together. So when we have 6 over 4, or 4 over 6, that's 2/3, then rho, then u average A, linear momentum flow rate. True? And so that's our linear momentum flow rate. You could put it like that. That would be good enough. And then by inspection, what is my momentum correction factor? I messed something up here. What did I mess up? Linear momentum correction factor shouldn't be 2/3. What is it? It's 4/3. Where did I mess up? You're absolutely right. That 2 was supposed to be squared because I took this u and I replaced 2 times u average. I deviated from my notes. And then it's 2 squared because this u average needs to be also squared, doesn't it? And so this is 8 u average squared. And so, yeah, I need that u average squared. So then let me boil down. This is now 4/3. We're fixing it. Thank you very much. And then this is u. Then I multiply by u average. All right, there we go. Linear momentum flow rate is, I should have even explained it a little further, is equal to 4/3 mass flow rate u average. There, finally got the right units and everything. So the the linear momentum correction factor is 4/3. And if you wanted to, you could put the linear momentum flow rate equal to 4/3 mass flow rate, U average. Whoever caught that squaring was good. Who did that? Very good. You never gave me your thumbs up. You didn't agree with my analysis, did you? You were probably chugging away saying, something's wrong, huh? Thank you very much. I appreciate that. Any comments or questions on this? Does it look good? All right, let's press forward. So we have velocity in a thin layer of fluid flowing down an inclined plane. So here's our plane. Here is the angle theta of the incline. And here is the wall or the plane that the fluid flows down. Here's that fluid. And what we find is that we have a velocity profile that's shaped like this, where it's 0, no slip at the plane, the solid surface, and then the velocity profile looks like this. Okay, so here is U. So what we have is a coordinate system where you have X and Y. Now I didn't put Y, I should put Y right here. So there's X and Y. Y starts from 0 and it goes up to H. So this thickness of the fluid layer is H. And what we find is U, the X component going in this direction, U, is a function of rho, the mass density, G, without some sort of gravitational sort of weight and of the fluid, the acceleration, you wouldn't have flow going down the plane. Sine of that angle of inclination, H squared, so the thickness of that fluid layer squared, divided by 2 times the dynamic viscosity of the fluid. And then you have this part right here, which is 2 times y over h minus y over h quantity squared. So I think we understand all those terms. Again, y is that distance measured from the plane into the fluid, and the fluid layer goes from y of 0 to y of h. Calculate the average velocity. That's part A. Let's just do part A, and then we'll move to part B and part C. So, let's do this. What is the maximum velocity first? Where, if this profile is shown correctly, and it is, the maximum velocity occurs when y is equal to h, true? So let's just say evaluate u when y is equal to h, and that will be our maximum velocity. If you do that, what do you get for a solution? Can you see that? It'll be 2 times y over h. Hey, that's 2 times h over h. That's 2 minus h over h squared. So 2 minus 1, 1. And so it's going to be just every coefficient, rho g sine of theta h squared divided by 2 mu. Isn't that the maximum? Yeah, that's the maximum. So in order to simplify a little bit, you get tired of writing this group of terms. You could replace this group of terms by what? U max or UM or some subscript on it. Okay? So the velocity profile U is equal to U max times 2 y over h minus y over h quantity squared. True or false? All right, let's calculate the average velocity. Well, how do I calculate the average velocity? So U average is equal to, I'm going to pause, you write it down. You tell me, how do I calculate U average? board. All right, well, let's just continue on. So this is 1 over a, the integral of u dA. Is that it? Yeah. That's all we're looking for? So I want to calculate u average. So what is 1 over, what is the area? What is the equation for this area? Now you notice for part B and part C, they have to specify per unit width for the first part A. But it's nice to introduce it, it'll cancel out, right? So let's talk about some per unit width. Is this kind of a good illustration of the depth into the third dimension, the W? Let's call it W for width. And then the area would be H times W. True or false? True. That's that cross-sectional area that the flow goes through. Then we have to do this integral over, well, let's put in the equation for u. I like just put u max times 2y over h minus y over h quantity squared. And then I have to put dA. What's dA? W times dy, where y goes from 0 to h. True? Look good? So what about the w's? Can we cancel the w's? Sure. So for part A, the widths cancel. But for part B and C, we'll calculate that per unit width. All right. So let's take out the u max outside the integral. So then I have the integral of 2y over h minus y over h quantity squared, all that dy. But I had this h right here. If I take that h and I put it inside, then I have the derivative of y over h. Do you see where that h went? This h right here goes under there. So then I can, instead of integrating from 0 to h, I can integrate, I can put, let a new variable x equal to y over h, so that y is equal to x times h, all right? So that I am going to integrate the integrand 2x minus x squared dx from y equal to 0, well, that's x equal to 0, to y equal h, that's, I don't even need this part, do I, is x equal to 1. So this makes the integration just a little easier. I'm going to pause. Did I set it up right? Do I have an error? Do you follow that? What is x? It's just a new variable of integration, but it made the integral a little simpler. True or false? You finish it. You finish it. All right, so I think everybody can do this. What do you have? You have x squared minus 1/3 x cubed. True or false? Evaluate 0 to 1, which gives you, well, I'm leaving out the u max, but you get the u max times, then you have 1 minus 1/3 minus a bunch of zeros, so it's basically 2/3 u max. Is that what you got? 2/3 u max. So that's what the u average is. U average is 2/3 u max. I want to not erase this, but I need to solve for the next one, which is the mass flow rate per unit width. Okay, well, what is the mass flow rate per unit width? Couple things you could do. You could say the mass flow rate is equal to, do this, rho AV. Does that seem reasonable? And this V is U average. All right, we just calculated U average. So is it equal to rho height width U average? Yeah. So the mass flow rate per unit width is equal to rho H U average, which is rho H 2/3 U max, which is rho H 2/3 U max is, I got to scoot up just a little bit to remind us, U max is rho G sine theta H squared over 2 mu. So you could put the answer mass flow rate per unit width is equal to rho squared G sine theta H cubed divided by 3 mu. Likewise, I guess I could have put this U average over here. I could have expanded it. 2/3 U max. That would be rho G sine theta H squared over 3 mu. Isn't that U average? 2/3 of U max. So there's a number of ways to write the answers. You ready to do the hard part? Part C. Linear momentum flow rate per unit width. But what's the linear momentum flow rate? What symbol do we want to use? M dot? No, we can't use that. There's a couple ways you could write it. Sometimes I'll write it like this. Linear momentum flow rate. I don't think that's in the textbook, but it makes sense to me. You have to have a variable for what you're trying to calculate, or symbol, right? Or you could say, well, isn't it beta M dot V average or U average? That's true too. Let's just leave it as linear momentum flow rate. And how do I calculate it? How do I calculate the linear momentum flow rate? What's the equation? Just like, I guess I should have done this too. Back up. What is the mass flow rate if I said I want you to use calculus? Well, I'd integrate with respect to area, and I'd have rho times U dA. That gives me the little flow rate, and I'd sum them all up over the area. True? Put the rho outside, then I have the integral U dA. That looks a lot like something I've already done. If I put an area here and 1 over area there, that looks a lot like something I've already done. And that's why I just jumped to rho A U average. Because that's what it is. It's rho A U average. But if you wanted to, you could go back and calculate again that term. So now, what is the linear momentum flow rate? Well, it's the sum over, you have rho U dA, that's our little mass flow rate, but it's not just the mass flow rate, it's the linear momentum flow rate. So I really have rho U squared dA. True? Isn't that the equation? Could I pull the rho out? Sure. Put an area here? Sure. Then I'd have 1 over area, the integral of U squared dA. True? Okay. So what is the, how do I make this integral? So I'll have a, let me just do it this way. Rho, the integral of u squared dA. Okay, that's rho times the integral of u max. My equation was 2 times y over h minus y over h quantity squared, because and that's u max squared. The dA is going to be h, no, not h, with dy, and you're integrating y from 0 to h. 0 to h. Did that make sense? Yeah, this is for the linear momentum flow rate. And the linear momentum flow rate. All right. Well, I guess I do want to put in an h here and an h over here. Right? So this term becomes d of y over h. True? And then I'm going to pull that w out, and so I'll have the linear momentum flow rate per unit width is equal to rho h times the integral, well, let me pull out the u max as well, u max squared, or maybe I'll make it clearer, put it u max squared. Okay, the integral from 0 to 1, 2x minus x squared, quantity squared, dx. Did I do that correctly? Can you do that integral? I would expand it, right? So instead of having something squared, I'd have a bunch of terms. It would be 4x squared minus 4x cubed plus x to the 4, integrate 0 to 1 dx. I pause. Well, everything else has to go for the ride. I left them all out in the front. Rho h u max squared. Okay, but I was focusing on that integrand, right? Does it look okay? Did I do the integrand fine or not? Did I have a mistake? And then I integrate. Let me try and put it down here. That'll be 4/3 x cubed. I left off everything in the front. I'm getting so anxious to get to the heart of it. Rho h u max squared. Okay. 4/3 x cubed minus x to the 4 plus 1/5 x to the 5th. Evaluate 0 to 1. True or false? Look good? So let me not forget rho h u max squared. Okay, got that. 0 to 1, that will give me 4/3 minus 1 plus 1/5. Oh boy. What is all of that? Yeah, 8/15. Rho h u max squared 8/15. Okay. All right. So what is our linear momentum flow rate? Well, somebody says I would like it in terms of U average instead of U max. So I replace U max by, here, go back up here. What was our relationship between U average and U max? U average, so recall that U average was 2/3 U max. Is that what we had? So I can replace U max by 3/2 U average. So I'll have rho h 9/4, that's 3/2 squared, U average squared times 8/15. This is a 3 times 3, this is a 3 times 5, so that becomes a 5 and a 3. and that goes to a 2. So I reduce it, and I have the linear momentum flow rate per unit width is equal to a rho h u average squared times 6/5. Well, this is equivalent, and it's whether or not you clean it up and make it look nice. You can play with the algebra and make it look nice if you like. All right. Here's maybe go this way. Linear momentum flow rate is equal to W times H times U average times rho times 6/5 times U average. Well, what is this term right here? That's m dot, isn't it? U average 6/5. So guess what? For this problem, linear momentum flow rate, didn't ask for it, but guess what beta is, the linear momentum correction factor is? 6/5. Close to 1. It's not, it's laminar flow. It's going to be further away from 1 than, and greater than 1 than other cases, but it's 6/5, which is, what is it, 1.2? 1.2? So 20% over 1. All right. That was a lot of math, wasn't it? You ready to press forward? Water exits at a 20 millimeter diameter stationary nozzle at 25 meters per second. 25 meters per second is the speed it comes out of the nozzle, and it's stationary. And the diameter here is 20 millimeters. Strikes a cart, but the cart is moving at a velocity of 5 meters per second away from the nozzle, not toward it, but away from the nozzle. The water turns 145 degrees, as shown, by the deflector plate, as shown. There's a number of parts to this problem, so let's just step it off. Part A is, what's the mass flow rate leaving the nozzle? Mass flow rate leaving the nozzle would be the mass density of water, 1,000. The area of the exit of the nozzle, pi d squared over 4. And the velocity leaving the nozzle. All right, so we can calculate that the mass flow rate leaving the nozzle is right at 7.854 kilograms per second. That one was pretty straightforward, true? But let's continue the problem now and say, we calculated that mass flow rate leaving the nozzle. Now calculate the force necessary to be applied in this backward direction onto the cart in the horizontal direction such that the speed of the cart is a constant at 5 meters per second, knowing that the velocity coming out of the nozzle is 25 meters per second and the water is deflected as shown. So how am I going to calculate the force F of H needed on that cart? The approach is to introduce a control volume. Now, we have choices of control volumes. They can be fixed in space and not moving, or they can actually be moving in space. But if they move in space with time, don't have them accelerate. It's too tricky. Go dig into the book and play with it. But you can have it where it's moving at a constant speed. It's not accelerating control volume. Which one do you want to employ? Let's move it with the cart. So let's move the control volume with the cart. So we have a cut here, a cut there, cut here, cut there, and it goes up like that. So now that we have this control volume introduced, and it's moving at constant speed, true, then we can worry about the fluid streams cutting here and cutting there. This is an in, this is an exit. The fluid's exiting, the fluid's coming in there. True? Okay. So we go and we say, let's do a linear momentum balance on that control volume. And we're going to introduce the x as the positive x direction, and this will be the positive y direction. So for the positive x direction, linear momentum, we have negative f of h. It's in the negative direction. We have no rate of change of linear momentum with respect to time. It's steady state. And then we have some linear momentum flow rate. I'm going to say Vx on the exit minus beta m dot Vx on the inlet. Okay. From conservation of mass, is the mass flow rate that comes out equal to the mass flow rate coming in? Are they the same mass flow rates? Yes. So we drop the subscript and we just say it's mass flow rate. So that's a little step of logic there, but the mass flow rate coming out of the control volume is equal to the mass flow rate coming into the control volume. It's just the mass flow rate that we're going to use in that linear momentum equation. Let me ask this. Is that mass flow rate that's coming into the control volume, is that what we calculated for part A, clicker question? Clicker question. We calculated from part A that the mass flow rate leaving the nozzle was 7.854 kilograms per second. True? And this mass flow rate that we need in this linear momentum equation, I'm going to ask, is it greater than 7.854 kilograms per second, equal to 7.854 kilograms per second, or less than 7.854 kilograms per second? Answer A, B, or C. And we'll turn it on. And you have 30 seconds. All right, so what do you think? Well, what is the velocity of the fluid that's flowing across this boundary in that direction? Is it greater than 25 meters per second or less than 25 meters per second? Well, the boundary of the control volume is moving with the cart to the right at 5 meters per second. It's cutting across only at 20 meters per second. It's cutting, the velocity of the fluid is only cutting across at 20 meters per second. Hence, it's flowing across at a lower flow rate. Remember, the cart's moving and the nozzle stationary. So the mass flow rate that I need to use in this equation right here is really the velocity that it's coming across the boundary of the control volume, and it's 6.284 kilograms per second. Okay? All right. Let me ask another question. I need to calculate Vx coming in. Vx coming in. Is that greater than 0, equal to 0, or less than 0? And all of those are in units like meters per second. Answer A, B, or C. Vx in. I'm going to put it right here in this equation. All right, we're there. Okay. Well, I think I said it in words, and I even said what it was supposed to be. Isn't it supposed to be 25 minus 5 meters per second? Isn't it supposed to be 20 meters per second? And so if it's 20 meters per second, that's greater than 0. Very good. True? So, but now let's do this one. Vx exit. What is that? Is that greater than 0, equal to 0, or less than 0? Answer A, B, or C. I have to put something right here into this equation, don't I? It's called Vx exit. Is it greater than 0, equal to 0, or less than 0? A, B, C. All right. The illustration is what's really helpful, true? This is the way the fluid is flowing. You're going to have to decompose that velocity vector into a component in the x and a component in the y. The component in the x is in the negative x direction. And so, isn't it C? What about the component of the exiting velocity in the y direction? It's in the positive. How about the velocity of the incoming fluid stream in the y direction? 0. 0, right? Okay, very good. So now the next question is, and this one requires an assumption. Okay. The fluid hits this plate and diverts. The cross-sectional area that fluid stream is operating over, it's a little bit of a stretch of an assumption, but it doesn't change. It doesn't change. The cross-sectional area of that fluid jet doesn't change. So if the cross-sectional area of the fluid jet doesn't change, the mass flow rate of the fluid jet doesn't change, the density of the fluid in the jet doesn't change. What about the velocity? Just the speed right here, not as a vector quantity, the magnitude of the velocity. V in versus V exit. Even it's just the speed. Well, we would assume that they're the same, and that's a big assumption. So the magnitude of the velocity coming in is equal to the magnitude of the velocity exiting. Or V in is equal to V exit. Now, so then what is the velocity on the inlet? Vx inlet, we said it was 25 minus 5. It's 20, true? So right here, this quantity is 20 meters per second, true? But now I can quantitatively evaluate this quantity. What is the velocity in the x component of the velocity on the exit? So Vx on the exit is equal to a minus velocity on the inlet, because that's the same as the velocity on the exit, times the sine or cosine of some angle. I can't figure it out. Help me a little. It'll be, you could put the cosine of 145, true, but then you would not need that minus sign. Or you could put the sine, the cosine of 35 with the minus sign, true? So either one, without the minus sign, cosine of 145, run it on your calculator, make sure they're the same, as well as with the minus sign, cosine of 35. So now, what about the betas on the inlet and the exit? Is there any information in the problem statement about the linear momentum correction factor? No. What do you assume? 1. So we just neglect betas. And so now we have an equation. I'll try and rewrite it over here. Negative force in the horizontal equal to negative the mass flow rate cutting across the control volume. Okay, that's with the cart, times the cosine of 35 degrees plus 1 times the velocity cutting across the boundary of the cart, something like that. And so this number is, we'll get rid of the negative signs. So f of h is equal to 6.284 kilograms per second. we'll just leave it the cosine of 35 plus 1 times 20 meters per second. And so F of H comes down to 229 newtons, units. You're familiar with kilogram meter per second squared as a newton. Well, we're done with this part, but there's probably another part. Guess what we're going to calculate next? F of V, that vertical force. So I think that's the next part. Let's go to it. So I summarize a lot of results already that we just worked out, so you can refer to them. We'll start with a clean diagram, and now we just want to solve for the force F of V. All right, I look at it. Is there anything about the weight of the cart? Anything at all about the weight of the cart given in the problem statement? And so you have to assume it's a weightless cart or negligible weight. We still have this control volume that cuts like this. Okay? And instead of doing linear momentum in the x, we'll do linear momentum in the y in order to solve for F of V. But I look at this and I see that the incoming fluid is just flowing only in the x direction. The outgoing fluid has some upward direction to it as well as backward direction. It's up and back. True? Can you just look at it from your experience? I know this is a hard question, but let me ask it anyway. F of V, and it's positive in the upward direction because that's the direction shown on the arrow. It's just like we have F of H was positive in the backward direction, right? Is F of V going to be greater than 0, equal to 0, or less than 0? Answer A, B, or C. What is the F of V going to be? Greater than 0, less than 0, or equal to 0? What is it going to be? All right. This is one of those tough things because we're going to talk about thrust in a minute, and it's on your perspective. What it is you have a force, F of V, that's external to the control volume, that's acting on the control volume to push upward. Now, if you had no fluid flow at all and you had the weight of the cart, wouldn't F of V equal to the weight? It would be like the weight down and F of V up. True? So we have to have the orientation of F of V. It's pushing up on the bottom of the cart. Now, what happens to the fluid? It comes in with no momentum in the y direction. It goes out momentum in the y direction. It had to be kind of pushed in order to gain that momentum in the y direction. Now you look at the reverse, you might think of it like this. I have the fluid stream and it's turning like this. The fluid stream will push on something that makes it want to turn. So the something that makes it want to turn, the vein, will feel a downward force pushing down on it. True? And then that has to be supported by something external. All of this is to say we anticipate the answer to be greater than 0. That's correct. Think of it, that's a good way of looking at it. If you do this, if you take that cart and all of a sudden you don't support it anymore from any external force, and it's turning that fluid and pushing it up, well, that is going to push the cart and everything else that the fluid's hitting against, pushing it down. Just like if you didn't supply this anymore, which way would the cart go if the water jet was turned on? The cart jet would accelerate in that direction. True? And here it would accelerate in the downward direction if you took away those supporting forces. All right. So now let's solve for and calculate F of V. So we apply the linear momentum control volume analysis for inlet fluid flow and outlet fluid flow for the control volume, and we have that negative, well, this is a positive F of V because it's in the upward positive y direction, is equal to, and then we're going to have the correction factor, the mass flow rate, and then I'm going to put Vy exiting minus mass flow rate Vy incoming. One of those is 0. Which group is 0? This second group. Then we have to work carefully to get this mass flow rate. This mass flow rate is not just what's leaving the nozzle. It's less. We talked about that. And then we have to be careful about what is the velocity in the y direction, and it's positive, leaving. Okay, so that is going to be the speed crossing the control volume times a sine of 35 degrees. And this mass flow rate is what enters, crosses the control volume. The beta, we put 1. Do you agree? So this should be the 6.284 kilograms per second times the velocity 20 meters per second times the sine of 35 degrees. Somebody want to run that for me? Oh, I got, yep, it's 72.08. 72.1. Thank you. Good?
Why is beta 0? 1, I'm sorry?
Beta, because we have no information about the linear momentum correction factor. It's really different from 1 if it's laminar flow. There's some regions where it's really slow and some regions where it's fast in the cross-sectional area. Here, we don't have any information. It's probably turbulent and close to 1.
So we just, like on a test, we would just assume.
Yeah, if you're not given it, you have to. You have to make an assumption. I know it makes students a little uneasy. You have to make an assumption. The best thing I can do is say, I'm going to assume if you have time. Because there's usually a lot of things you have to assume on a test. But yeah, you'd say I'm going to assume beta equal 1. So we're all done with that problem. We've solved another problem like this before. Do you want to solve it or do you want to skip it? I got a couple other. I got to get in the angular momentum, so maybe we'll skip it. Here, I want to talk a little bit about thrust before I get in angular momentum. Let's do this one. A rocket burns a fuel at a rate of 2 kilograms per second, and the combustion products are ejected from the rocket with a velocity of 1,300 meters per second. So you could put the rocket either horizontal or vertical. You could put it like this, or you could put the rocket like this. It really doesn't matter. But what we're trying to show is that somewhere in here you have some combustion or some, yeah, it's combustion. And then what exits the rocket is some very high speed products of combustion. Okay, and so they exit, V exit at 1,300 meters per second with a mass flow rate of 2 kilograms per second. Now, from your experience, think about the horizontal case first. If I have a rocket that's sitting there like that, which way will the rocket move? It'll move horizontal, and will it move? Should I have the clicker question? Nah, it's too easy. It'll move to the right, will it not? Yeah. All right, it'll move to the right, okay? Because it's propelling stuff to the left. And so if you do analysis using our control volume right here, that's our control volume, and we do a linear momentum analysis, let's go ahead and write stuff down. We'll have that we have any forces acting on it. Well, I don't know. Let's just say that there's an unknown force acting on it, F, in the positive x direction, okay? Equal to time rate of change of the linear momentum in the x direction in the control volume. So we'd integrate over the control volume of the density times the u dv. So that's the term we very rarely use, but if you have the momentum changing because the rocket's now accelerating, you need to include it. That's the accelerating part of the linear momentum in the control volume. Plus, we have that integral over the control surface, which we break down into inflows and outflows. And in this case, you'll just have an outflow. I'm going to put a beta there because it's always there and we assume it's 1. The mass flow rate exiting and then the velocity exiting. Okay, in the x direction. This is x component exiting. True? So this is determined, the thrust force acting on is just going to be at an instant of time. I'm not worried about it. Accumulation and depletion of the linear momentum in the control volume. And so this force is equal to just, and this is 1, is equal to the mass flow rate at which it exits, right? Times, what about this here, this velocity? Is it a positive or a negative quantity? It'll be negative 1,300 meters per second. I should have put in this mass flow rate is 2 kilograms per second. True? So we find that it's 2,600 newtons. Well, for this system to not accelerate, that means that the direction of the force that I have to apply on the system is in the wrong direction, isn't it? I'm going to have to apply a force that's in the negative direction, right? To keep it stationary and not accelerate. True? Well, if you apply no net force on it to keep it stationary, it's going to start moving. It'll start moving as if there was a force applied to it to make it move. And so it'll start moving as if there's a forward thrust. And that forward thrust is equal to the mass flow rate times that exit velocity. It's equal to 2,600 newtons. It's one of these perspectives. I have a rocket, it starts burning, it starts throwing out fuel out the back end. It's bolted to bottom of a wing or whatever it's bolted to, if it's a jet engine or something in a model airplane or something that's going to, it's going to push that object forward with a forward thrust. If I want to not let that rocket move anywhere, I'm going to have to apply a force to counteract that forward thrust and push it back or hold it stationary.
And that's what we're calculating for, is to hold it in place. Basically.
So I basically calculate to hold it in place, turn it around and call that thrust. That's right. All right. Here's another problem. I have a jet engine. It ingests 25 kilograms per second of air. So here's my jet engine. Fancy looking jet engine. And we have air coming in here. The mass flow rate of the air coming in is 25 kilograms per second. And inlet speed, V inlet, is equal to 200 meters per second. And which direction is it? Well, this is the positive x direction, okay? And so that's equal to Vx in, and it's positive 200 meters per second. And then on the exit, we have exhaust gases come out, and you probably have a little fuel comes in and sprays in combustors, so that the mass flow rate going out is a little higher. It's 26 kilograms per second instead of 25. So 1 kilogram per second of some mass came into the system. Guess what the mass balance says? The mass flow rate of some fuel is 1 kilogram per second. Is it coming in with any significant linear momentum in the x direction, the mass flow rate of the fuel? Nope. But it's adding to the outgoing linear momentum flow rate on the exit because it's coming out at a spanking speed of 950 meters per second. Okay. Determine the thrust force produced by the engine. So we'll say that we introduce a control volume. And we would say for this engine to remain stationary and not, let me say, if I don't hold it, if I don't restrain this engine, the way it's set up, this is a clicker question, the way it's set up with no restraint, the engine will either move to the right, move in that direction, or it will move to the left in that direction. Answer A or B. I don't restrain the engine. It can move this way or that way. Which way, if I fire that engine up, is going to start moving? Without restraint. Pardon? Okay. For fear that one or two people got this wrong, let me break this down here. Anybody ever been like an air hockey table? You know how it slides, it's almost frictionless, right? Let's say that you could get yourself on a big puck on an air hockey table and it's completely frictionless. And you're sitting there you are, and you have a big bucket of basketballs, pretty heavy, or a big bucket of bowling balls if you're really strong. All right? So I'm going to take that big bucket of bowling balls, and as fast as I can pick them up and as fast as I can throw them, I'm going to throw them with a hefty speed in that direction. I'm going to pick up a basketball, pick up a bowling ball out of that bucket and throw it, boom, that direction. I'm on an air hockey table. I know it's hard to vision that, but there it is. Do I just sit there or do I start moving? If I start moving, which direction do I start moving? You're going to start moving this direction. True? Conservation of linear momentum will prove that or show that or demonstrate it. That's a discrete system where you're throwing them off. Now look at, if you had here's another question for you. If you were in a race with a friend, right? And you said, okay, you have a choice. You know, I will give you a bucket of ping pong balls and I'll take the bucket of basketballs. Who's going to win? Of course, the bigger mass that's being thrown out, right? So if you can really whip the high-speed mass with a large V, a lot of linear momentum flowing out, you're going to go and accelerate, and you're going to feel the net effective thrust force. So here, there's a lot more mass going out at a much higher speed. Not a lot more mass, but there's some more mass, but a lot higher speed, a lot higher linear momentum flow rate. Which way is it going to push it? It's going to go to the left. It's going to start moving out. To hold it stationary, what direction is the force going to be needing to be applied to this system to hold it stationary? To the right to hold it stationary. So if I put that under a wing of an aircraft, here's my wing of my aircraft, the wing of the aircraft is going to feel a force in the opposite direction, the equal magnitude. And then we're going to call that the thrust force. The bottom of the wing feels the thrust force when that engine's running. True? But the way we calculate the thrust force is we consider what's necessary to hold the thing stationary. And it's in the opposite direction of what the wing would feel. All right, so we do this control volume, so we have force thrust that's in the positive x direction is equal to, we have the, forget the beta, we have the mass flow rate and the Vx exiting minus the mass flow rate, the Vx incoming. This is 26 kilograms per second times the 950 meters per second minus 25 kilograms per second times the 200 meters per second. And can somebody please run that for me? Is it 19.2?
It's 220. We wrote it down. Well, it's not 200. The original is 220. The question
Oh,
is
yeah, there's my mistake. Okay, so it's 220 and 220, thank you, which then changes it slightly to 19.2. Close. Thank you very much. Thank you very much. Whoever caught my error. Let's talk about angular momentum. So we go back to Reynolds transport theorem and we say it's not mass, it's not linear momentum, it's angular momentum. But we have to remember, what is angular momentum? I think I already did a little review of that. You can have the angular momentum about a point, true? And it's, if I come out here to R and I have a little chunk of mass m traveling at speed v, what is my angular momentum of that point mass m traveling at instantaneous speed v located at position r as a vector from the origin? It's r. True or false? That's what it is, isn't it? And I know that we like to work with vectors. I know we like to work with cross products. I know we like to work in 3 dimensions. But often, before we really become super sophisticated with all the cross product and the vectors and all that, we want to make sure we can talk and deal with scalar analysis. So when you look at cross, this is just R cross M and the tangential component. It's you replace that cross product by just a multiplication.
mass or mass flow.
That's a mass here. This is, I'm just looking at a chunk of mass. I'm doing a little review of dynamics. Okay. So, and this V is the tangential component. So we would decompose into a tangential component. Maybe I shouldn't use that color, but this one right here, such that it's 90 degrees. True? Makes sense? Yes? No? Okay, well, that would be the angular momentum of that particle around there. So anyway, you have what changes angular momentum? Moments. Moments change. So instead of sum of forces, you have sum of moments. And then you could have a change of the angular momentum in the system. Almost always this is 0 because we operate in steady state conditions. And then we have the angular momentum flowing out and the angular momentum flowing in. Yes, it's R cross m dot v, but we often just say, hey, some sort of shaft is rotating. It has some torque in it. That torque is my moment that's driving the system. And we have the mass flow rate. If you just have one inlet and one outlet, we'll call inlet state 1, outlet state 2. It'll be that perpendicular distance R2 from the shaft about which it's rotating times that tangential speed leaving, that fluid stream leaving at location 2. And it'll be also the same for 1. It'll be some perpendicular distance between the axis that the shaft is rotating and the fluid stream where it's entering, coming in at state 1. And then it'll be the tangential component coming in. Ready to solve problems? Great review of dynamics. True? Start out easy. We have a water sprinkler that has one straight sprayer. So this is where it rotates the shaft. There's a little thing up here to help distribute the water down this one tube or one shaft, and then at the end it opens up and fluid comes out. So fluid comes in, then fluid goes out. And this thing is, the tip of it's moving in an arc, right? Maybe I look down on it and miniaturize it so I can look down. Here's the small, it comes in, here's this tube coming out, and the fluid goes out like that. And this whole thing is rotating. Around what axis? That axis right there. Okay? Now, they have some dimensions. The length is 200 millimeters from the center line where it's rotating to where it exits out. Yeah, it's like a radius, 200 millimeters. And we have the diameter of the exiting D is equal to 8 millimeter diameter. And it has a mass flow rate of 0.25 kilograms per second of water. All right, calculate the steady torque needed to keep the sprinkler rotating at a steady 30 RPM. So this is omega, it's 30 RPM. Which way is it showing to rotate? This is a positive Z direction, so to speak. If you take your right hand, it's in the positive K. K as a unit vector around that Z-axis, or in the direction of the Z-axis. And so it's a positive. If we were looking from the perspective looking down this way, if we look from the top and we see it rotate that way, true, we would say it's rotating in the positive counterclockwise direction. All right. So we're going to have a torque. Is the torque going to be also in that positive direction, or is the torque going to be in the other direction? It's a torque that's being needed to be applied. Though the whole thing is moving, it's moving at 30 RPM. It's rotating at a constant speed. Right? All right. So let's assume that t is in this direction. If we calculate a negative, then we know it was in the opposite direction of what we assumed. So let's assume it's in this positive direction. So we introduce a control volume, and then we apply our balance or conservation statement of angular momentum to that control volume. Now, that control volume can move and rotate with time. So let's, just like we could have a linear constant motion of linear motion with our control volume, you can have a constant rotational motion with our control volume. That's what we're going to do. So our control volume is going to be something like this. It'll cut right here because I like fluid cutting across the boundary of our control volume. It'll come up through the air, out through the air, out through the air. It'll cut right there through the fluid stream that exits that control volume. Air, 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 close it. And I know that I'm showing a 2D control volume, but think about it as 3D. And closes and cuts where the fluid cuts at two places, coming in and going out. Now, that control volume has an axis, and that control volume is rotating with omega around that axis. True? So you could think of the control volume as cut here, come back, go there. And that control volume does rotate with the same speed. All right. Let's apply our angular momentum equation. So what do we have? Torque applied. True? It's in the positive Z. We'll leave it with a positive. Equal to nothing with the transient. I'm just going to say, hey, that's steady state, so throw that out. It's not accelerating or decelerating. It's moving at constant speed. All right. Mixed. Oops, that's not an equal sign. we're going to have some coming in. Well, what is the in? It's going to be, let me do this one. Mass flow rate, R, V tangential on the exit. Sorry, that's an exit. Minus the mass flow rate, R, V tangential on the inlet. Okay? All I did was take the equation and try to apply it to this problem. One of these group of terms is 0. Either this group or this group is 0. Which group of terms is 0? The inlet. And why does the inlet have no angular momentum flow rate around the axis? It's going right along the axis. It's like, go back to dynamics, and they said, here's my axis, and here's my particle, and it's moving in an arc around the axis, going in a circular motion. Yeah, it has some angular momentum flow rate. But if the particle's moving this way, parallel to the axis, it may have some linear momentum, but does it have any angular momentum about that axis? No, because it's parallel. True? Even though it's offset. But in this case, it's not only parallel, but it's along the same line as the axis, so it's like its perpendicular distance is 0. So both reasons lead that the incoming is 0. Now we take a look at the outgoing. Maybe it's good from this top-down perspective. The fluid leaves the end of that nozzle, and it's just a straight shot out, radially out. True? Okay. Well, what is R? Well, R looks to be like 200 millimeters. But what is V tangential? Well, we already know the mass flow rate. That's 20.25 kilograms per second. But what's V tangential? That's exactly right. So if you looked at it, you say the little chunk of fluid, when it leaves this tip, yes, it's coming out relative to the tip with that speed. But the tip is also moving in that direction. The tip is sensed so that the speed of the velocity of the fluid leaving the tip is, you have to add them both up, and that's its total speed. One, because it's shooting straight out, but the out is also rotating, so I have a rotational component, and so the net speed is at an angle, not straight out. Okay? So this is V tangential. And V tangential really doesn't matter what the flow rate is or the diameter is. What's it depend on? V tangential is omega, the rotational speed, times cap R, a lot of times cap R. So in this case, it's omega, the 30 revolution per minute, times the 200 millimeters. That makes sense? So the torque, steady torque needing to be supplied to this is 0.25 kilogram per second, 0.2 meters, 32 pi divided by 60 to convert radians per minute into revolutions per minute into radians per second. And this is second. And this is 0.2 meters. And what do you pick up for that shaft? We're going to pick up a kilogram meter per second squared is a newton, but then we have a newton times a meter, so that's our units for the torque. What do we get for that answer? 0.0 0.0314 Newton meter. Let me see if other people agree. 1, 2, 3, 4, 5. Looks good. 5 people agree. Okay. All right. That seemed like a pretty simple application. But if we wouldn't have remembered that the tangential speed is omega r, we would have said, hey, I don't need to supply any torque. It'll just rotate like that and fluid will just come out the end for nothing, right? But what's happening is you have to supply torque to have it rotate at a constant speed because it is coming out with both a radial component but also a tangential component, which means it has some angular momentum. Thank you very much. Send me information about problems you want to see solved for Thursday. And then we're going to solve problems out of the previous 3 chapters and get ready for the test on Friday.
We're doing those